do?
Like this.
Hold up.
Good afternoon. Welcome. Okay. Indeed. Alright. So, we should probably get going here. Ha! Too much stuff around my room here. Alright, Kelvin and Hobbes, yes. So, how are we all doing today? A couple of little announcement-y type things for you all. So, been kind of keeping an eye on the GVSU subreddit and listening to chatter and all that fun stuff. No, this is kind of a fairly stressful time for everybody, what with everything, plus finals start on Monday. So what we will do Friday is we'll do another Zoom session. It will be very similar to last time where, yes, there is a GVSU sub. They had some people asking if 350 was going to be okay or not at the beginning of the semester. But yep, there's a sub for it. And basically what I wanted to do is to have kind of a low stress kind of a day for you all rather than have brand new material that's coming out on the last day of class. Basically to be a similar, let's work through finalizing everything, work on your requirement specs, prep your presentations, get all of your ducks in a row for the end of the semester. Basically, get everything in line, be able to ask me questions, things of that nature. Pizza party day. Hey, maybe we could do got I don't know, pizza slices and standard emotes anyway. Yeah, something like that, basically. So it'll be on Zoom. I'll post the link in Blackboard when we get to there. Other things, so I put up the assessment for your team that I mentioned last time that's due on, I think it's Wednesday or Thursday I made it due. But basically it's just kind of the follow-on to last homework's evaluation where make sure that everybody who was kind of falling behind is hopefully caught up. And if you haven't caught up because for whatever reason, you have that big chunky software requirements spec coming up due, so put in some effort there if you're looking for work to get done or help everybody clean up or whatever you got to do. But goal is to basically evaluate your teammates on their contributions and things of that nature. And my suggestion for all of you here would be to be honest. because, honest feedback is going to be better than, blowing smoke up somebody's behind. That doesn't teach them anything. Um, but that is up there, and again, that will be another individual thing for you all to do. So just basically like number evaluations and then a little paragraph at the bottom for reflection on the class and the term project and all that fun stuff. Other thing, presentations are Monday, right? So that is when we have our final exam. Not all of our tests have to pass, right? Correct. The active testing is what we're trying to get here. Ideally, you would fix it, but if you're not fixing it, that's for the next release. But yeah, that's as long as you're testing, I'm happy. You don't have to post meeting minutes this week, last week of class, so I think you're all probably at the state where you don't need to post them anymore. And yeah, presentations are on Monday, so if you are coming in not realizing that our final exam slot is technically Monday, I forgot to put it in the cheat sheet front thing there, so it is at 12 to 2 p.m. Yeah, do one for yourselves too. I didn't have that in there, but that would be ideal, yeah. So 12 to 150, basically. We'll do everybody's at once, limit it to 15 minutes, and we should all be fine. I will add this to Blackboard. Funny thing is I did this for the morning class, and I did this live as well, realizing that I probably should have done it beforehand, but hey, everybody gets the same experience, right? Blackboard, final presentation, 12 to 150. All right, so that is there. What else? So I graded your last homework assignment. You still have the one prior that I'm working on. It's taking more effort to grade than I thought it would. But I at least got your Travis CI assignments graded and all of that fun stuff. So if you are missing like a massive chunk of points from that, please read your feedback because there's a good chance that either you forgot something or you made your repo private and I couldn't actually access your source code. So I give you a little bit of a grace period if you screwed up in that matter. But just kind of check the feedback for that. All right. Other than that, we can roll onward. So again, Friday's on Zoom. Monday is the presentations, and then all your deliverables are due basically at the end of the week. Just check the deadlines to make sure. Okay. So a little bit of a refresher for all of you. Last time we talked about black box testing, started getting into white box, right, with the knowledge of what's going on inside of a program. Talked about branch coverage, condition coverage, started getting into basis path testing. Anybody remember the difference between branch and condition coverage, though? And I guess if you get all your homework done tonight, isn't Cyberpunk 2077 dropping tonight or tomorrow or something like that? You get all your work done so you can play? Lunch is tonight at 7. There you go. And here I am still playing Spelunky and Noita. I think I've been checking out. I don't know that my computer could handle Cyberpunk. Branch coverage maps out the if-else branches. Yeah. So branch coverage is giving you the notion of checking paths of execution, right? Checking all the various branches there. So condition coverage is similar to branch, but different, right? Yeah. Spelunky 2 did come out, RTX 3080. I've got an RTX something on here. It's a laptop version, though. But finally got to Abzu in Spelunky 2. That was fun, and then I died shortly thereafter. Okay, so branch coverage, true and false at least once, condition every, yes, exactly. So again, keep in mind that when you have a branch, it is possible to check all of the branches of execution even though not all of your conditions are checked, right? So if you have an if statement or a loop of some kind, it is possible that not every condition is accounted for. However, all branches will get executed, right? They will all be followed. So that is one thing that you have to consider with that. So branch coverage, path of execution, condition coverage, checking your conditionals. We also had multiple condition coverage. That's where you bring in your ands, your ors. Basically, you have multiple conditions, and then you're checking all of those variants for that. So it's basically, again, kind of getting you towards that idea of making sure everything is accounted for while still not doing exhaustive testing. Right, so let's see, we ended about here, right? So we were drawing flow graphs of our programs. And if you remember, basically we're creating nodes in a graph which are going to correspond to some program statement. The edges are the paths of execution from one line of code to another. And we just called these edges, or sorry, these nodes, we just had them correspond to the line numbers, right? So line 1 is here when we actually start doing something in our code. Right? We skipped over the declarations that are just creating memory space for us. So again, here we have path of execution. We have a loop because of this while. And then once we're done with the loop, we go to the return statement here, right? Pretty straightforward. What we have to do after we figure out this graph, and the one thing I should mention too, again, very simplistic program that you're seeing here, this can get way more complicated. And these kinds of graphs can be automatically generated. You know, there are tools that are baked into, or can be baked into, say, Eclipse or Visual Studio or VS Code, where you can automatically get these graphs. You can even generate them on the command line for C or Python or something like that. You end up with a, it's like the dot format, I believe it is, and then it's kind of turns into a PDF. It's in some fashion. But basically, we're going to have these graphs, right? And we can analyze them, again, either manually or automatically. So we have that graph. Next step is to figure out the cyclomatic complexity. So this is a very big term, and all it really means is how many unique paths of execution are there in your program. And again, your program can be a function, can be the whole thing, can be a set of modules. It's whatever you're focusing on, right? Now, the cyclomatic complexity, you can calculate it in multiple ways, and we'll look at 3 different ways to do that. And all this is really telling us is how many test cases do we need to fully check this program to make sure that every path is executed at least once. So complexity is just paths of execution. All right, so if we look here, how many paths of execution do we have? We have 2. We go from line 1 to 2 to 3 to 6, right? Because this branch evaluated as false. We also have 1 to 2 to 3 to 4 to 5 to 3 to 6. So we have a second path of execution, right? So we go down through this loop, and we can loop any number of times here. This particular perspective doesn't care how big the loop is because it's always going to be the same. We just know it's a different path of execution. So we go loopy, 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 and then we bail out. Right, so it is technically a different path because we have unique edges in this particular line of execution that we have there. So cyclomatic complexity will be independent paths, and how do you figure that out? With 3 very simple formulas. They ideally should all evaluate to the same thing. Right, so the first one is going to use the enclosed regions method. It's just how many enclosed regions do you have plus 1. What's an enclosed region? Well, it's going to be something where you have a fully encapsulated region, right? So it'd be like a little bubble or a loop in your program where we have this enclosed region, right? So you can see consider this space here to be enclosed. So there's 1. 1 plus 1 is 2. We have 2 paths of execution. Makes sense. Second way to do it. Use the edge, use the nodes. Number of edges minus the number of nodes plus 2. There's your complexity. So basically 6 edges, 6 nodes. 6 minus 6 is 0, plus 2. 2 paths of execution. All right, I've got the visual here, and we'll walk through that as well in a moment. Third way. Again, these are 3 separate functions. You don't necessarily need to use them all unless you want to make sure they all agree with each other. how many predicate nodes do you have? Add 1 to that. Well, yes, what's a predicate node? Well, predicate node, thank you for asking, is a node where you have 2 or more paths leaving it. Right, so here you have node 1, 1 path leaving. Node 2, 1 path leaving. Node 3, you have true or false. There are 2 paths leaving it there. That is a predicate node. All of the other ones here just have 1 edge leaving it. So, number of predicate nodes, 1. 1 plus 1, 2. So here we have 2 independent paths in our program. Again, these ideally should all agree with each other. Now, I'm sure there will be cases, and I don't have one off the top of my head where they disagree. But again, what you're trying to get here is kind of like an upper bound on how many test cases you have to write. And if you look at this program, and again, it's super simple. Your programs are all going to be way more complicated than this. You're trying to figure out how much effort you have to put into testing this thing. And when we're talking about cyclomatic complexity, figuring out the number of paths, again, this is white box testing. You know what's happening inside the program. You're trying to exercise it to see what happens when you follow each particular path of execution. So you go back to last time, if you have code that's not executed, that's a problem. You don't know what it's doing. But if you test it out, you can actually demonstrate, yes, this block of code does this, this, and this. So we get here, cyclomatic complexity of 2. That means we basically have a maximum 2 test cases we have to write to trigger these loops, right? How do you follow this path? It's going to require some input conditions. Okay, how do we follow this path? Input condition will be different. All right, so with that, we get that value of 2, then you have to figure out what the paths are that you have to follow, right? So which are the paths? And here you can do this, again, manually or automatically. So basically just trying to figure out what are the unique nodes and edges that you are following here. Right, so the set of paths is called the basis set if you're looking for the formal definition. But kind of the important thing is what comprises an independent path is that you have to at least have one edge that is unique in every single set of paths that you have. And what I mean by this is that here, let's build up a set of paths here. Right, so 1 to 2, 2 to 3, 3 to 6, that is one path. Right, these are the edges in our first set. The second set, the second path also has those edges, right? But we add in this loop here, and that makes it a unique path. And I'm kind of staying on this intentionally because intuitively I'm saying this to you, and you're like, yeah, that's really simple. Of course that makes sense, right? You have 2 separate things that look different. But if you're making this happen automatically, all you have to do is look at, say, a list of paths. Maybe you define a path as an array of, edges with IDs. Maybe it's a JSON object or a dictionary or something like that, or a linked list. This kind of looks like a linked list anyway, right? You have arrows pointing to nodes and all that fun stuff. But just look and see, is there a difference between path 1 and path 2? If yes, it's a unique path. So that's all you really have to do there. So we have our graph, we have our cyclomatic complexity, and very simple calculation. I assume you can all do addition. Reuse my joke from the first class. If you, hopefully nobody saw that. We have a calculator app team. If you don't know how to do addition, feel free to use their app for that. Last step here, figure out what test cases you need to trigger these paths. Excuse me. So what do we have? We have 2 paths. We have 1 input value, right? This input value is n. It's an integer. Okay, so what are we going to do to n to trigger 2 separate paths? Well, where does the path occur? It occurs at this while loop. The while loop is basically a glorified if statement, right? You have a conditional thing that's happening here. If I is less than or equal to n, do the loop. If I is greater than n, do not do the loop. So that's where your branch happens. And if you're writing a test case for this, you have to just trigger the loop to be true and it to be false. So how do we trigger it to be true? Well, if it's true, I is less than or equal to n. I starts out as 1, so basically n has to be greater than or equal to 1, and that is a test case. You could have any number of those test cases and you know procedurally what the output will be, right? And what's the other side? Well, if I is going to be greater than n, you're never going to hit this loop, meaning you will go down this path of execution. So if we set n to say 0, right, it's not going to trigger the loop. You follow that other path of execution. And what does that tell you from a programming perspective? Well, you are basically verifying your algorithm that you have here for summing numbers, right? And again, simple program, but you could be doing this for any type of complicated program or simple program. You're exercising it by trying out all your different paths. So here's your two test cases. N is less than or equal to 0, expect that the output is 0. N is greater than or equal to 1, your expected result is going to be the sum from 1 to whatever you feed into it. And all of the outputs should be relatively easily verifiable, right? This would be a test case that you could write. We may have another hidden path here too, which isn't really described in our program, and that's more related to the actual structure of the things here too, though. N is an integer, meaning that it is bounded in how much it can hold, right? So if we start getting up to, say, I don't know, the upper bound of what an integer can hold, like 2 to the 32, this program is going to break, right? Because we're either going to have a segmentation fault, if we're in something like C or C++, Java, I have no idea how it would handle it, but it would probably complain in some way, shape, or form. Python would just die out, I believe, on the terminal. But you have a kind of hidden path of execution where things break because you're not upper bounding it. Not really captured by the cyclomatic complexity here, but just kind of one of those things to worry about. And that's what a tester would expect to try out. But again, that's not really the focus of path testing here. We're just trying to exercise the program. This is more me telling you other things to watch out for. Alrighty, everything making sense so far? And if not, just remember, basis path testing is pretty simple 4 steps. Create your graph, figure out cyclomatic complexity, figure out what the paths are, and then write the test cases to trigger those paths. Again, something that can be easily automated if you're looking to avoid manual labor here. But if that makes sense, let's walk through at least I think a fairly simple example, but still kind of, a little bit more complicated than the last one, but a good one to talk about here. So we have a factorial function. Factorial, something you probably learned hopefully early on, that is a good example of recursion. But we're cheating, we're not doing recursion here, we're just doing a while loop. But we have some conditions to make sure that we don't have bad values coming in. So what do we have? We have a factorial function, line numbers copied basically right out of a ver IDE or TextPad or whatever you want to use, just kind of tacked on here for easy identification purposes. And again, if you're looking at this and not really sure what's going on, I seem to have lost my VS Code instance that I was looking at. Let's just look at this very quickly. So line numbers on the side just correspond to whatever line you need to talk about for your program, right? When we're generating our graphs, again, we don't really care about the function invocation. We don't necessarily, well, the invocation we care about, the actual declaration we don't care about. The variable instantiation we don't necessarily care about because we're not doing anything other than allocating memory. We'll just kind of take it as granted that that's fine. But here we start actually doing things, right? We have a if statement, we have an else statement, while loop, bunch of stuff going on here. So how would you draw this graph? Again, we're going to start at line number 3 because that's the first time we're actually doing anything programmatically, like doing actual either assignments or decisions or something of that nature, right? So we start at 3. First thing that happens at 3, we have a branch. We have an if statement, right? So we have if n is less than 0, return well, set fact to 0, return 0, basically. Right, so we have a if n is less than 0, by getting to line 4, we have seen that whatever's coming in is less than 0. Go right to our return statement there. So, bop, bop, bop. One path of execution. Easy peasy. Second one, from 3 to 6, meaning that n is greater than or equal to 0, right? So we start at 3, line 3, n is not 0, or it's greater than or equal to 0, sorry. So we go right to our else block, and then we do stuff in here. So go from 3 to 6, set I equal to 1, line 7, fact equals 1, line 8, oops, while loop. So we have another decision here, right? So while I is less than or equal to n. Again, this is another branching statement. So either I is going to be greater than n, in which case we immediately bail out, or I is less than or equal to n, in which case we go through this loop multiple times, or however many times it takes. Eventually, it flips. Now I is greater than n, bail out, go to line 13, which is return whatever our calculation was here, right? So straightforward factorial function turned into a flow graph here. A little bit more complicated than the last example, but still, in the grand scheme of things, really, really simple. These can get extremely complicated. And one thing to note too, if we were in class, I'd have you all break out pen and paper and draw this out. This bubble goes to here, here's this edge, this edge, this edge. This is a lot easier in some kind of a tool like, a draw.io or OmniGraffle or Visio or something like that, where you can have these nodes connect to other objects and you can very easily move them around and have the lines resize and, hook onto other objects, because these can get very, very messy. Actually, let me, just for funsies, let me do a quick diversion into Google Images here, because that's always a great idea. Complicated flow graph, or program flow graph. Let's see. Here we go. This one's a little bit more complicated. I think this is a class diagram, actually. But you can kind of see how these can get very, very messy very quickly. Why am I not seeing any actually complicated ones? Here's a good one. This actually has a little bit more going on to it. Signal flow graph, so similar, but basically there's stuff happening on the edges. But you can kind of see how these can get more and more complicated. All right, so we've got our graph, meaning that we are ready to move on to calculations, right? So before we move ahead, I'm going to leave it here. Okay, that's good. Pointer back. So again, we had 3 ways to calculate things, right? We had counting the nodes and edges, counting the enclosed regions, counting the predicate nodes. I'm going to do that really super quick here. How many enclosed regions do we have? We have 2, right? Here's 1. Fill this guy in with the darker background. You have 1 enclosed region. Here's your other one. So we have 2 enclosed regions. How many predicate nodes do we have? Those are, again, our conditional nodes, right? So here we have 1. 3 can go to 4 or to 6. We have another one down here at 8. 8 can go either to 9 or 13. So you have 2 predicate nodes. So we can calculate this out very, very easily. Enclosed region, number of enclosed regions plus 1. 2. Again, 2 enclosed regions. 2 plus 1 is 3. Edge note. So we have 9 edges. We have 8 nodes. 9 minus 8 is 1. 1 plus 2 is 3. 3, a cyclomatic complexity of 3 there as well. Last one, predicate node. How many predicate nodes do we have? We have 3 and 8. They're both predicates, meaning that we have 2 of those nodes. 2 plus 1 is 3. Hey, our cyclomatic complexity values all agree, meaning that we have 3 paths of execution. Again, simple example, simple math, but very powerful for what you're doing here. Yeah, I agree. So basically, the thing to keep in mind is this can get very, very complicated and messy. So sometimes it's easier to use one versus the other. I don't have a good example offhand of where these would disagree, but I'm sure there are possibilities where these values don't always give you the same answer. I've got to look into that a little bit more. But I mean, just think of like a messy, doubly embedded, triply, quadruply embedded region, and just gets kind of ugly quickly. But yeah, 3 passive execution, right? So 3 to 4 to 13, 3 to 6 to 7 to 8 to 13, 3, 6, 7, 8, 9, 10, 8, 13. Straightforward. What does that mean? Well, we need 3 test cases, right? So how do we get from 3 to 4? Let's go back to our factorial here. How do we trigger these paths of execution? Well, to get from 3 to 4, we need to set n to be less than 0. So pass in n is -1. So your expected output then is 0 because you've got that being returned, right? Input -1, output 0. Does your test case pass or not? Second path. So let's say let's go from 3 to 6, and then let's bail out here. So that means that n is greater than or equal to 0, but I has to be less than n. So we kind of have a double conditional that we have to test for here, right? So I is going to be set to 1, meaning that I has to be greater than n to skip this loop. So if we set n to be 0, we can get into this conditional, or sorry, into this branch here, but we can skip the while loop, meaning that we go down this way, right? So for n equals 0, that's your second test case. What's your expected output? Well, fact is going to be 1, so you would return 1. Third path, anything greater than 0, right? Because you get into this branch, you get into the loop, and then your expected output would be whatever the factorial of that value is. And that's something you'd calculate out manually by hand. Or you'd have an assertion to check that or something of that nature. But 3 paths of execution, hopefully pretty straightforward for you. If we were having an exam, I would definitely expect you all to be able to do this very, very easily. Not that complicated of a subject. At 1:30. So we have static V&V to talk about. We have debugging and then a little bit more of an example with Travis. So that was white box testing. We talked about black box testing before. You underestimate how dumb. No, I always expect the best out of everybody, and 4 times out of 10 I get the best. Oh, I know. I've been teaching for a while. I understand that sometimes topics or concepts just don't get through. But all of you are perfect. All right. So let me pop all these up on the slide here. So everything that we have been talking about up to this point has mainly been focused around your implementation for testing, right? We've been doing black box testing, checking the inputs and output values, which is effectively what you're all doing on your SRSs, if you think about it. White box testing we just talked about, verifying paths of execution, making sure that your program gets a good dose of exercise in. But consider all of these artifacts that you've been creating, right? Your software requirements, your UML diagrams. These are all manually generated, more or less, meaning that there is the capacity for human error to occur in every single one of those as well. And the thing you have to consider when you're writing software is that you are writing it to, writing it to your specification. So if your specification is bad, your code's going to be bad. If your spec's bad, your test cases are probably bad. Because you are writing that software to this ground truth, this golden document that specifies your behaviors. But if there are problems there, well, you will implement it as it's written down. So typically there are going to be processes in place to actually check your requirements, check your artifacts, right? Check your class diagrams, your state machines, your use case diagrams, whatever it is. You can basically go through this whole process with these artifacts as well. So we can have an informal process, which would be more of a walkthrough where, okay, you give everybody a copy of the artifact, whatever it is, and say, hey, we're going to walk through this. Let's check and make sure everything is correct and complete and makes sense. No spelling errors, everything's clear and concise, describes exactly what it has to be doing. Simple walkthrough, right? Get your team together in a room, informally talk about it. That identifies some of the easier, lower hanging fruit type problems. You can have a formal, rigorous inspection too, right? You get everybody prepared, you walk them through what the document is, you give them copies, read it over the course of the week, mark everything up, check it out, come back on Monday, and we'll all lock ourselves in this conference room or virtual conference room now and walk through every single one of these requirements. Make sure everything makes sense. More formal, rigorous process where at the end you check off, yes, this is done, we all approve it, enter it into your configuration management tool, and lock it down, right? What if you discover problems? Somebody typoed. Somebody said the word private instead of public for a particular variable. Well, go through a reworking process. Fix the artifact, enter it back into your config management tool, go through the process again until everything is set in stone. So again, everything about engineering and software is about a process. Whether you're following waterfall or agile or whatever it is, you're probably going to have a rigorous process to follow. Artifacts follow the exact same rules. Go through, write them, implement them, test them, in this case, verify them, and just keep going until everything is good. You can also do a desk check where basically you just have one person kind of informally reading through, making sure everything makes sense. Not as strictly formalized as the inspection type process, but still very relevant. You can catch a lot of the easier issues that way. Maybe you have a smaller quality department and desk checking is all you can afford. But again, kind of the idea here is however you're doing it, make sure that you check them. Okay. All right. So, last point here, which we are not going to get into, but there is a lot of kind of interesting research you can get into, is formal correctness. So, everything we've been talking about so far has basically been like manual evaluation, right? Looking through, do things make logical sense or is it correct? You can actually turn your artifacts into mathematical objects, like turn a requirement spec or a class diagram or a use case diagram, turn it into a formal mathematical automata of some kind, run a model checker on it, right? Are there any conditions in which these requirements are invalid? Basically, you run a very rigorous, formal mathematical proof type of environment. And as long as you can represent your artifact in this particular language or construct, you can actually get like a formal mathematical specification saying these requirements are good or they are bad and you need to fix them. Some industry has kind of latched onto this, but it's pretty well entrenched in academia and research at this point. So I wouldn't go thinking you need to go run out and learn mathematical proofing for software engineering, but there's a good chance it's on the horizon if you stick around with software engineering. Just something to be aware of. And if you're looking for terms, if this interests you, there are languages like spin or alloy, um, linear temporal logic. These are all used in mathematical proofing for software engineering. Okay, so let's say that we have found a problem somewhere, whether it's in your implementation, test cases, in your requirements, anywhere, doesn't matter. Do you have any examples? I don't have any on hand because I really am not a formal software engineering person, but let's say Alloy software engineering. This is going to be tiny, blurry text, isn't? Oh, guide to Alloy. There you go. So here you go. This would be a Alloy's like pseudocode. It's actually more like formal logic. So it's pseudocode, but it's its own thing. So here, basically, you have a puzzle. So effectively, you're specifying some problem, and it turns into basically like a model or a state machine type of thing, where you would, in this language, you talk about facts and signals and abstractions and things of that nature. This state connects to this state, connects to this state. and your goal is to figure out, are there any cases where your model breaks down? It's called a counterexample. In that case, your model is broken and you have to fix it, right? There should not be an example where some set of data breaks your model. Again, this is getting into the more formalized advanced software engineering. You can bring in things like timing and correctness proofs and all kinds of crazy things here. Alloy is one of the more newer-ish types of ones. Spin and Promula are like the older versions of that. Honestly, Dr. DeVries is really into this area, so if you want to bug him about that, if you have him for class, you can tell him I sent you and make him explain all that. Again, I'm more of the validation person. I like the testing. He's into the model checking stuff. But no, I'm more than happy to chat about it after class too, if you want. Outside of class, I should say. I've done a little bit with it, a little bit enough to know that it's not doesn't excite me as much. I can definitely see the place and use for it though. All right, so what do we do for debugging? This will vary from person to person, environment to environment, but at its core, you're trying to find the root cause of some problem. And again, it could be code, it could be a requirements issue. What are you doing? You're trying to work out what this problem is. And how do we debug things? You're probably all taught to use a debugger, to do trace debugging where you print out got here, LOL, oh crap, we should not be here. Look at variable values, trace through, do a stack debugging or stack trace or something like that. Debugging can be as easy as talking to a rubber duck. I know some of you have discovered that. But honestly, just talking out your problems to some inanimate object, it kind of crystallizes the picture in your head of what your problem is. Basically, you're just talking it out, right? You're talking to a party, in this case, rubber duck or something like that. Obviously, this is Coochie Copy. But yes, there you go. You're just talking through a problem. And you can do this to real people too, right? Because maybe a real person could help point out flaws in your logic, or maybe assumptions that you're making that you didn't actually realize that you were making. But if you do it to a rubber duck or some, thing on your desk, they won't judge you or tell you that you're wrong or talk back to you. But that's one way to do it, right? Talk out your problem. Bring in a third party. Absolutely works well. And yeah, so there's that. You can also honestly just brute force it where, again, print out variable values, watch a variable in a debugger. I would highly recommend learning how to use debuggers too, because they exist for pretty much every programming language. C, Java, Python, JavaScript. There's a baked in, gotta get out of full screen for that. There's a baked in debugger in the browser if you're doing web development. Come on, don't do me dirty like this here. There we go. Hey, look at that. Here's my console. I could actually look at the code and set debugging frame or breakpoints. Here we go. You gonna let me do this? Probably not gonna let me do this. But you can set breakpoints right in your browser if you're debugging JavaScript, for instance. So we have that. But honestly, the key takeaway is, how do you zero in on the problem? Do you talk it through? Do you brute force it with a debugger? Do you do something a little bit more elegant, like localize it to a particular set of use cases and try to work backwards? The key is that you will find problems and you have to figure out how to solve them. Okay? And debugging is how you do that. It is not the easiest or most exciting process. It's probably more mind-numbing because you thought you were done, then you discovered a problem, and you have to take all your time and put it into fixing the problem. But it's a necessary part of everybody's job. All right, last thing I want to show you for today, I wanted to kind of go back to this Travis CI tutorial and show you the coverage aspect of it, because we only did the unit testing part. So if you look at the guide, I point to this person's repo. I'm just going to use it as a brand new thing, like I was doing it from scratch here. So I'm going to fork this repo into my my account here. And we now see this, let me zoom in a bit, this code coverage metric here. So 71%. There, somebody's hammering something into the street right outside my window. Must be a snowplow company or something. All right, irrelevant. Here we see 71% code coverage. We'll get to that. All right, what do we have going on here? We have a travis.yml still. And what has changed is that we are now doing something after a build is successful. And it's reaching out to this website, codecov.io, which is a code coverage visualizer, basically. So if we go here, it's another third-party API, which looks at your GitHub, looks at your Travis, and says, hey, here is your coverage metrics. All right, so we have that. This person uses Maven for their build, so we have a pom.xml. And I am not doing anything in here other than showing you it, but we actually have a plugin call to Jacoco, which, if you remember, I mentioned this is the coverage tool for Java. It'd look different for Python or C++ or something like that, obviously. But this agent will be brought in to analyze the code coverage of your test cases. But don't have to touch it. It's there nicely set up for us. Life is good. Source code is all the same. No differences there. And what I'm going to do here now is I'm going to actually add that repo into my Travis account. And password, and we need to get this Travis repo. Grant you access. Then we have a Travis. So again, same thing that you all did before, right? Nothing crazy here. What I'm going to do now is I'm going to update this README file, which again is specified right in the tutorial if you want to try it out. I'm just going to update the tags from, this person to my name. So Travis, it's now E. Fredericks, E. Fredericks, check her back in, and call it good. All right, so I updated it to me. These are probably gonna, well, disappear eventually here. But I should see, did I? Do we need a hot second here anyway? Oh, yep, thank you. Glad somebody's paying attention here. It's clearly not me. Yeah, I heard a little bleep. That means that I probably got a test passed. Or somebody did something. There we go. All right, so we have our unit test running again. Same thing that you all did. Check, add, subtract, multiply, divide. Nothing crazy here. This should hopefully run quickly. We actually had a problem with this in the morning class. It didn't grant codecoverage.io access until later on. Okay, so our build passed. Good, good. If I refresh this, it's probably going to say, well, okay, hopefully that's good. Build passing. Good, good, good. Still alive. All right, I'm going to click this code coverage badge here. This will take me to codecov.io. Again, a separate website here. This is where things broke down for me. Might have to give it a few minutes. But we see that coverage metric of 71%, and this was the problem. Yeah, so this is what happened last time. Honestly, like, giving it 5 minutes fixed the problem. Let's try to refresh it a few times, see if it picks up. Yeah, I did copy and paste it into Discord. Let me pull that up. And of course, Discord's gonna black screen on me because it hates multiple graphics cards, apparently. Come on, Discord, get it together. All right, Discord, have you fixed yet? No, okay. Let's go back to Discord here and I'll sling this over. Actually, I don't want to bring Discord up into the stream just in case. Paint. Sure, why not? Paint 3D. This is what we should see. Um, and this will probably update after class would be my guess, because that's just how it goes. So now let's see if it, no, all right, fair enough. So this is what you would see in the code coverage tool. Now, it's looking at my unit tests here, right? Or sorry, it's looking at my actual calculator class, and we're seeing that we have coverage on our test case or on our various functions, right? Because we've written test cases for them. If you remember, we're instantiating add, sub, mult, divide, but we're not actually doing anything with main. So that means that we are never touching this line of code, right? If you run your test cases straight up, you never see hello world, meaning that we don't have full coverage of our code with our test cases. So that's kind of what you can get out of an automated code coverage tool. What code is never checked by your test cases that you've put in? This is kind of where the power of continuous integration can kind of help you out here too, right? You build up your test case library. Ideally, it's exercising your program either in terms of unit tests or even branch testing, coverage testing, whatever testing you like. So with that, all I've got for you today. Friday, again, will be on Zoom if you popped in late. So other than that, I will see you all Friday. Hope you have a wonderful day, and good luck prepping for finals week. It's probably going to be a lot of fun. All right. Bye, everybody. Thanks for popping in, chatting. Always fun. See you next time.